Chengcheng from the University of Tennessee. Today I'm glad to present our work, Online Knowledge Distillation by Temporal-Spatial Boosting, on behalf of Wang and Hairong Qi. Why do we need knowledge distillation and online knowledge distillation? We know neural networks have achieved significant success in a wide range of applications. However, these neural networks are usually huge and their deployment on resource-limited devices is difficult. Knowledge distillation has been proved powerful method for network compression and acceleration. Knowledge distillation trains a compact network, referred to as student, by imitating the soft targets generated by pre-trained large networks. Classic KD relies on pre-trained networks as the teacher, which is not always available. Online knowledge distillation fills the gap by training student peers that learn from each other from scratch. Our work is built upon deep mutual learning, where student networks are trained simultaneously in a peer-teaching manner. Peer networks, also known as students, treat each other as teachers by learning from their predictions via Kullback-Leibler divergence. Online knowledge approaches is a highly dynamic procedure. Each student network learns its parameters from scratch and meanwhile acts as an instructor for other networks. Training with developing instructors tends to involve more uncertainty. Our objective is to stabilize the training process of online knowledge distillation and therefore improve the efficiency of knowledge transfer. This figure shows the framework of the proposed method in the context of image classification. Built upon the classical deep mutual learning framework, we introduce two novel modules, the temporal accumulator and the spatial integrator. The temporal accumulator takes the historical predictions and current prediction as input to generate an accumulated prediction as to the transferred knowledge. The spatial integrator takes in the predictions from all students and generated an enhanced prediction as knowledge. The loss function for optimizing each network is composed of three components. LCE represents the cross-entropy loss between the network's outputs and ground truth labels. LTA and LSI are the KL divergence of the network's outputs and the results of the other peer's temporal accumulator and the spatial integrator, respectively. The main idea of the temporal accumulator is to leverage historical predictions via exponential moving average to provide a superior teacher. For each temporal accumulator, we have a container Z that contains the accumulated predictions of network theta I for all training samples. Accumulated predictions are calculated with equation 2. The spatial integrator integrates the predictions of all student networks as an extra enhanced teacher at each iteration during training. In this work, we define the integration function G in equation 3 as averaging. We evaluate our approach with several benchmark structures and datasets. The proposed method is compared with several state-of-the-art online KD methods, including DML, KDCL, 1, in terms of top 1 test accuracy on CFAR 10 and 100. The two students have identical and different structures in the right and left table, respectively. We observe that the proposed method consistently outperforms the state-of-the-art methods in most cases to different degrees. In this ablation study, we evaluate the effectiveness of each proposed component by comparing the performance of the following configurations: DML, DML plus temporal accumulator, DML plus spatial integrator, and DML plus temporal accumulator plus spatial integrator. We observe that when introducing either temporal accumulator or spatial integrator to the DML, the performance increases considerably in all experiments. Besides, when using both components, the performance is further improved. We continue to study the effect of EMA decay beta, which controls how many previous predictions are involved. We consider RESNET32 and WRN16.2 on CFAR 100. Beta varies from 0.1 to 0.9 with a step of 0.1. It can be observed that when beta equals 0.8, the best performance is obtained for both architectures. That is, approximately averaging over 5 epochs. To better understand the effect of these components in stabilizing the online training process, we visualize the test loss and accuracy of our method and DML over the training epochs, with ResNet32 and WRN16.4 on CFAR 100. We find for both networks, the test loss and accuracy curves of our method are smoother, showing much fewer spikes compared to DML. In the end, I'd love to summarize our study. We presented a novel method for online knowledge distillation. Temporal accumulator and spatial integrator were proposed to provide superior instructors for student networks during the training procedure. Several experiments were conducted to validate its effectiveness. Thank you for watching.